This is SpaceTime Series 20 Episode 1 for broadcast on the 4th of January 2017. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, claims that the universe has lost up to 5% of its dark matter. NASA's Juno spacecraft completes its third close flyby of Jupiter. And the Quadrantids meteor shower is now underway, providing a spectacular light show for sky watchers. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The universe may have lost up to 5% of its dark matter since the Big Bang. The findings reported in the journal Physical Review D could explain one of the big mysteries of physics, namely why the universe appears to behave slightly differently now compared to shortly after its formation 13.8 billion years ago. In the process, the new study could also shed fresh light on how the cosmos itself is likely to evolve into the future. The research by a team from the Russian Academy of Sciences is based on the study of the cosmic microwave background radiation, the leftover heat from the Big Bang, which is now cooled to just 2.7 degrees above absolute zero. By studying the cosmic microwave background, scientists get a snapshot of what the universe was like 370,000 years after the Big Bang, a period when the cosmos had cooled enough for protons and electrons to come together for the first time to form the very first hydrogen atoms. Slight temperature fluctuations measured in the cosmic microwave background point to tiny differences in the structural density of the universe at that time, allowing scientists to glean information about the conditions the very early universe experienced. By measuring these differences in the remnant radiation, researchers were able to calculate key cosmological parameters. However, it turns out that some of these parameters, namely the Hubble constant, which describes the rate of expansion of the universe, and also the parameter associated with the number of galaxies in clusters, vary significantly compared to data from observations of the modern universe obtained by directly measuring the speed of expansion of galaxies and studying clusters. What all this means is that some of the key cornerstones of physics, important constants of science, such as the speed of light in a vacuum and the way gravity works, may have been slightly different in the past. To try and explain these discrepancies, the authors looked at both the composition of the universe today and also the way it was 13.8 billion years earlier when the cosmic microwave background radiation emerged. Data from the European Space Agency's Planck Space Telescope tells us that the mass-energy budget of the universe consists of just 4.9% normal matter, the stuff stars, planets, cars, houses, trees and people are made of. A further 68.3% is dark energy, a mysterious force apparently working opposite to gravity to cause the universe's expansion to increase at an ever-accelerating rate. And the remaining 26.8% is dark matter, a mysterious substance which has mass but is invisible and can only be detected by its gravitational interaction with ordinary matter. Astronomers first suspected there was a large proportion of hidden mass in the universe back in the 1930s. That's when astronomer Fritz Zwicky discovered peculiarities in a cluster of galaxies in the constellation Coma Berenices. The galaxies were moving as if they were under the influence of gravity from an unseen source. This unseen source was given the name dark matter because no one really knew what it was. In fact, they still don't today. The authors in our study analysed the Planck data and compared it to different hypothetical models of dark matter to try and explain the observed differences they were seeing between the modern universe and that seen in the cosmic microwave background, which represents the very ancient universe. They specifically focused on two dark matter models: the standard lambda cold dark matter model, in which dark matter is stable, and the decaying dark matter hypothesis, which states that the early universe contained more dark matter than it does today, and that some of it had decayed. They found they could best explain the discrepancy between the cosmological parameters in the modern universe and those of the universe shortly after the Big Bang if there was a decrease in the proportion of unstable particles in the composition of dark matter immediately after the Big Bang compared to today. The authors say dark matter should be thought of in the same way as ordinary matter, which consists of a range of different types of particles, such as protons, electrons, neutrons, neutrinos, quarks, and photons. If you think of dark matter in the same light, then one component of dark matter may well be an unstable particle with a rather long lifespan. Now, these hypothetical particles would have been around in the era of hydrogen formation 370,000 years after the Big Bang, in other words, the cosmic microwave background. However, those same particles have all decayed away by now, 13.8 billion years later. As to what it was they decayed into, well, maybe they've become neutrinos, or some hypothetical relativistic particles. Now, if this is the case, the amount of dark matter during the era of hydrogen formation would be different to what it is today. However, while the decaying dark matter hypothesis model is more consistent with the observational data, the authors found that the effect of gravitational lensing, in other words, the distortion of cosmic microwave background radiation by a gravitational field, greatly limits the proportion of decaying dark matter in the model. Using data from observations of various cosmological effects, the team were able to give an estimate of the relative concentration of the decaying component of dark matter in the region of around 2 to 5%. The authors aren't able to say how quickly this unstable dark matter component decayed, or for that matter if it's still disintegrating today. What they can say is that there's up to 5% less dark matter in the universe today compared to what there was at the time of the cosmic microwave background radiation. You're listening to SpaceTime. I'm Stuart Gary. NASA's Juno spacecraft has successfully completed its third close flyby of the planet Jupiter. At the time of closest approach, known as perijove, Juno skimmed just 4,150 kilometres above the gas giant's rolling cloud tops, travelling at a blistering 57.8 kilometres per second relative to the planet. 7 of Juno's 8 science instruments were operating and collecting data during the flyby. Juno's principal scientific investigator, Scott Bolton, from the Southwest Research Institute in San Antonio, Texas, says it was the first time scientists were able to use virtually all of Juno's full array of science instruments to investigate Jupiter's interior structure through its gravity field. That data is now being downloaded, and Bolton says the research team are looking forward to see what Jupiter's gravity may be revealing about the gas giant's past as well as its future. Only one of Juno's instruments, the Jovian infrared auroral mapper, wasn't operational during the flyby. It was deliberately left off so that mission managers could complete an update of the spacecraft software that processes the auroral mapper's data. A software patch allowing the mapper's operation is expected to be available prior to the next perijove pass. Mission managers are also continuing to weigh up their options regarding possible modifications to Juno's orbital period. In other words, how long it takes the spacecraft to complete one orbit around Jupiter. At present, Juno's orbital period is 53.4 Earth days. NASA says the spacecraft is in good health and performing nominally despite the intense radiation environment bombarding the ship. And that's where Juno's highly elliptical and elongated orbit comes in. It's designed to avoid as much of that radiation as possible. To further improve the reliability of the spacecraft's most sensitive instruments and systems, they've been placed in a special radiation-resistant safe, which provides some additional protection. There had been plans back in October to perform a period reduction manoeuvre with the spacecraft's main engine to reduce its orbital period from over 53 down to just 14 Earth days. But mission managers made a decision to forego the manoeuvre in order to further study the performance of a set of valves which are a key part of the spacecraft's fuel pressurization system. The orbital period reduction manoeuvre would have been one of the final scheduled burns for Juno's main engine. The Juno spacecraft was launched on an Atlas V rocket from the Cape Canaveral Air Force Base in Florida back in August 2011, achieving Jovian orbit insertion on July 4, 2016. During its mission of exploration, Juno soars low over the giant planet's mysterious cloud tops. During these low-level flybys, Juno will probe beneath the obscuring cloud cover of Jupiter and study its auroras to learn more about the planet's origins, structure, atmosphere and magnetosphere. Juno's name comes from Roman mythology. The mythical god Jupiter drew a veil of clouds around himself to hide his mischief. But his wife, the goddess Juno, was able to peer through the clouds and reveal Jupiter's true nature. I'm Stuart Gary and this is SpaceTime. Well, Beijing still won't admit it, but it seems one of its two Long March 2D rockets has placed two new and very expensive Earth observation satellites into the wrong orbit. The 42-metre tall Long March 2D blasted off from the Taiyuan Satellite Launch Center in Jiangxi Province before heading south across mainland China towards the South China Sea. The mission was carrying two of Beijing's newest and most advanced high-resolution Earth observation satellites, as well as a small CubeSat. China's state-run media are reporting the mission as a success, but independent observations by the United States military indicate the satellites have been placed into the wrong orbit. It appears they were deployed into a 524 by 214 kilometre high low Earth orbit instead of the 500 kilometre high Sun synchronous orbit intended. The mission appeared to be going according to plan. The Long March 2D's core stage, which uses a liquid-fueled YF-21C engine, burnt for its fully allotted 3 minutes until MECO or main engine cutout and first stage separation, all of which appeared to go nominally. The second stage YF-24C liquid-fueled cluster engine then ignited for its 7-minute burn just as expected to take the satellite payload into orbit. The mystery surrounds what exactly did happen when they reached orbit. The two primary payload spacecraft, SuperView 101 and SuperView 102, are the first of a new generation of civilian multi-sensor commercial remote sensing satellites being built by Beijing. Now, assuming that they can be moved into their planned orbits over time, they'll be joined by two more identical spacecraft, SuperView 103 and SuperView 104, which are slated to launch around the middle of the year. This initial constellation will eventually be positioned 90 degrees apart, allowing them to provide good coverage of the entire planet. Each of the 560 kilogram satellites are capable of imaging an area of over 700,000 square kilometres a day, with a high resolution down to just half a metre in panchromatic mode and 2 metres in multispectral mode. As well as the primary payload, the mission also carried the BY-70-1 CubeSat U2 project for amateur Chinese radio operators. This is SpaceTime. Time now to turn our eyes to the skies and check out the celestial sphere for January on Skywatch. January can always be a tough time to go out skywatching. Not only are most people still recovering from the holiday period, but those of us in the Northern Hemisphere also have to deal with cold winter nights. Still, if you're willing to brave the chill, the rewards are there to be seen. And the best of those are the Quadrantids meteor shower. Most meteor showers appear to radiate or come from recognisable constellations, like Leo's Leonids, Gemini's Geminids, and Orion's Orionids. But the Quadrantids are meteors that appear to radiate out from the location of a former constellation that doesn't exist anymore, the Quadrans Muralis. The problems all began back in the 1920s. That's when the International Astronomical Union divided the sky up into 88 official constellations. However, that meant more than 30 other historical constellations didn't make the cut. The Quadrans Muralis area of the sky was instead usurped within the boundaries of the official constellation Bootes. The radiant point of the shower is near the Big Dipper, between the end of the Dipper's handle and the quadrilateral of stars making up the head of the constellation Draco. The Quadrantids are usually one of the most spectacular meteor showers of the year, with up to 80 meteors per hour. They're best seen from the Northern Hemisphere, and you'll need to be quick because they're at their peak right now. Also, unlike other meteor showers, which usually tend to peak for a day or two, the Quadrantids only peak for a couple of hours. And while most meteor showers are produced by the Earth passing through the debris trails left behind by comets, the Quadrantids are one of just 2 meteor showers produced by asteroids. They're associated with the asteroid 2003 EH1, which is thought to be the remains of a cometary nucleus which broke apart and fragmented centuries ago. EH1 still circles the Sun in a 5.5 Earth-year-long elongated comet-like orbit which extends out beyond Jupiter. The progenitor, thought to be the comet C1490Y1, was first observed by Chinese, Japanese and Korean astronomers some 500 years ago. It was classified as an asteroid when it was rediscovered by the Near-Earth Asteroid Telescopic Survey in 2003. The only other major meteor shower associated with an asteroid are the Geminids, which occurred in December, and are caused by debris from the asteroid 3200 Phaeton, which is also thought to be the remains of a comet. Now, speaking of comets, Comet 45P Honda should be visible about now in the evening skies to those with a telescope or a good set of binoculars. It's not very spectacular, but will still be there as a faint, fuzzy circular blur. Look for it low in the western sky just after sunset, although that will change during the month, eventually becoming visible just before sunrise in the lead up to February. Comet 45P has a nucleus estimated to be between half a kilometre and 1.6 kilometres wide, and it's on an elliptical orbit, pretty typical for a comet, with a period of 5¼ Earth years. First discovered back in 1948, Comet 45P will make its closest approach to Earth on February 11th. Also visible throughout January is Vesta, the brightest of all the asteroids. After Ceres, it's the largest of all the main belt asteroids between Mars and Jupiter. It'll reach its peak brightness on January the 17th, when it will be in opposition. Vesta's easy to find, just use Gemini's twin stars Castor and Pollux as a guide. Jonathan Nally, editor of Australian Sky and Telescope magazine, joins us now for the rest of our tour through the January night skies.
Yes, well, this time of year, of course, is beautiful summertime down here in the south, and it's characterised by beautiful clear skies. We never have any storms or clouds or cyclones and things like that, do we? No, perfectly clear skies all the time. The only problem, of course, is that for some of the country, we're on daylight saving. Now, some people love daylight saving, other people absolutely hate us. The sky gets dark when it wants to get dark, right, which different times of the year, but in summertime now, so we've got longer hours of daylight, shorter hours of night time, and you put that together with how we fiddle around with our timekeeping system.
And it affects the cows.
I think the cows fade, don't they, because of the sunlight, and the chickens don't get milked at the right time, that kind of thing. So, yeah, daylight saving messes people up, but look, if you can handle all that, it's a really good time of year for stargazing because, yeah, typically clear skies, and also you go out stargazing and it's warm. You know, it's not freezing cold like it is during the middle of winter. So anyway, let's get started. So starting down in the south, as the sky gets dark in the evening, and the Southern Cross is way down low towards the horizon, and it's upside down. Okay, a little bit more of that later on, but at the moment it's down low and upside down. Also visible down south, if you have dark enough skies, are the two Magellanic Cloud galaxies. Now, they're up reasonably high. If you've got dark enough skies, you can get out and have a look at them. They just look like little tiny fuzzes in the sky. It's best to try and don't look directly at them. Just sort of look to the side, look out of the side of your eye. That's called averted vision. It just makes
That's a little
light,
astronomer's trick.
Yeah, a little astronomer's trick. It makes the light come into a certain part of your eye that's more sensitive to faint things at night time rather than the bright daylight, bright colour sort of stuff. So you see if you can have a look at those. They're about halfway up from the horizon to the point directly overhead. About halfway up, that's the two Magellanic Cloud galaxies. The bright star you can see high up in the southeast is called Canopus, and this is one of the brightest stars in the sky. I think it's the second brightest star in the sky. The brightest star in the sky, Sirius, is nice and high up in the east, and a little bit around west from it, or around to the left, is the constellation Orion, which is nice and high up there in the north. We've spoken about Orion lots of times on the program. Our favourite constellation, we all know that. Lots of bright stars, plenty of great things to see if you have a telescope too, if you get it onto Orion. In fact, if you have a telescope, or even just some binoculars, follow the line of the Milky Way, our galaxy, from way down there at the Southern Cross in the south. Just sort of go from there in a straight line pretty much up to Sirius and then beyond, and just have a look, just scan up and down through the Milky Way, particularly if you've got nice dark skies, and just see how many nebulae and star clusters you can spot, because there are plenty of them. Now, planet-wise, Venus and Mars are the ones to see in the west after sunset at the moment. So if you go outside after sunset, you can't miss them. Venus is the big bright white one, and Mars is the dimmer British one. So that's Venus and Mars out in the west after sunset. If you want to spot Jupiter, you can, but you have to stay up a little bit later. At the moment, it's rising about 1 o'clock in the morning. That's in the beginning of January, and by the end of the month, it'll be rising at about 11:30 p.m., which is not too bad. Now, right next to Jupiter, and you can't miss Jupiter, by the way, out there in the east as it's rising, because it's a big, bright, white-looking star, inverted commas, but of course it's the planet. Now, right next to it, you'll see a bright star called Spica, and this is the brightest star in the constellation Virgo. Now, as you look at the two of them side by side, think of this. Jupiter is about 800 million kilometres away from Earth at the moment, right? 800 million Ks, it's about 500 million miles, right? 800 million Ks. Spica is 2,300 million kilometres away. So it's 3 million times further away than Jupiter, okay? And they're not that different, it's not that very different in brightness. Jupiter, of course, like all the planets, shines in reflected light from the sun, whereas the star Spica right next to it, that is actually a star 2,300 million kilometres away, 250 light years. So it just gives you a sense of perspective of, gee, Jupiter's a long way away, but that star is a very long way away, and 250 light years in the universe is just nothing. That's just right next door.
Down the road.
Just down the road. Now, both Saturn and Mercury, the planets Saturn and Mercury, have been lost in the sun's glare for a little while, so we haven't been able to see them. But they're starting to reappear now in the pre-dawn sky out to the east, right, before the sun comes up. So wait until the middle of the month, Then go out about 5 o'clock if you want to spot them, or maybe you're up already going for a walk, or you're about to start work or something, and you should be able to see them really easily out there in the east if you've got a clearish horizon, not too many buildings and trees and things in the way. Saturn looks like a bright yellowish star, in inverted commas. Mercury will be lower down on the horizon, and it'll look like a tiny but reasonably bright star, in inverted commas. They're not stars, of course, they're planets. Now, if you're out at that time in the morning, if you're up and around about 5 o'clock or so, particularly if you were outside looking at the sky in the evening the night before, have a look to the south, and you'll see that the Southern Cross, which when night fell was upside down and close to the horizon, is now standing the right way up, high up in the sky, okay? Now, it and the other stars haven't moved, of course. It's because the Earth has rotated that they've seemed to change position. That's a really good thing to do, actually. If you go out sort of as the night gets dark, have a look for some stars like the Southern Cross, something that's easy to spot, and then if you're up early the next morning, go out and have another look, and you'll see that they've moved their position. They haven't moved, of course. It's just that the Earth is rotating, so it's a really good way of demonstrating to yourself that we're not sitting on a static planet.
For our listeners who are in the United States or Great Britain, somewhere like that, and not in the southern hemisphere, is it a really different sky they look at night?
Well, it certainly is as far as the stars are concerned, because, depending on which latitude you are, either north or south, you can only see 90 degrees that way or 90 degrees down that way, north or south. So if you lived on the equator, right, and you lived on top of a hill on the equator, then you can see all the northern sky and you can see all the southern sky as well, or at least all of the north and south that happen to be visible at that time of year. But during the course of the year, you can see everything. But if you live at 50 degrees north, then you're going to see all of the northern sky, but you're only going to see some of the southern sky. Same thing if you live, say, in the latitude of Sydney in the southern hemisphere, which is about 30-odd degrees south, you're going to see all of the southern sky, but only some of the northern sky. So star-wise and constellation-wise, unless you live on the equator, then you're only going to get all of this one and some of that.
What about
all
the
of
planets?
The south, some of the north. Planets are the different thing, okay? So whether you're north or south, you should be able to see the planets. Doesn't matter whether you're the north or south, but it'll change how high above the horizon they might be. So certain times we might say that, Venus is up nice and high, and I'm saying that from the perspective of someone who's looking from the southern hemisphere, but from the northern hemisphere it might be that it's a bit lower, or vice versa. It just changes. So you can certainly take the planet section of what I talk about as being more or less the same, but sometimes I might say things like, okay, you've got this here, and if you look a little bit around to the right or a little bit around to the left, well, it might confuse people a little bit from the north and south. So yeah, basically what I say is from the southern hemisphere perspective. But at the moment, say I was talking about Jupiter rising about midnight or so during this month, January. So that's rising in the east about midnight. So if you go out, whether you're in the north or south, you're going to be able to see Jupiter coming up in the eastern part of the sky. Same thing with Saturn and Mercury, but with Mercury being so low on the horizon, if you're very far north or very far south, it can change how easy it is to see some of these planets sometimes. It's all to do with the angle of the plane of the ecliptic, which is the plane that all the planets orbit around the sun, and the angle that makes to our horizon. And that angle changes during the year. It's not that anything's changing out there in space. It's because our planet's axis is tilted, and that doesn't line up with the plane of the ecliptic. The long and short of it is, Stuart, what we see in the north, what we see in the south planet-wise is more or less the same, but you might get better view in the north or better view in the south, just depending on the particular planet at the time of year.
With the ecliptic, I always find the ecliptic simply by knowing where to look in the sky for where the sun and the moon would normally be, and that's roughly the area where the ecliptic is.
That's exactly right. And if you want to, here's a little trick also, if you want to find out where the sort of celestial equator is. You've got the south point down there and the north point up here. The celestial equator, particularly this time of year when Orion is up nice and high, you've got those three stars in a row in the middle of Orion, and they are basically right on the celestial equator. So you would know that if you lived on the equator and you looked directly up, Orion would be right over the top of you with those three stars in a line. So that gives you an idea too of how far north or south you can see at any particular point. If you happen to fly somewhere or you're on holidays or in your ship in the ocean and you don't really know what your latitude is, well, if you can spot Orion at this time of year and you can see it's either up really high, you think, okay, well, I'm very close to the equator here, or if it's down really low, you think, well, I'm far south or I'm far north.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter and Tumblr. Just search for SpaceTime with Stuart Gary.